Thank you. Talking about joint seminars, one of the most exciting intellectual experiences of my undergraduate life was a successful joint seminar run by Lakatos and Feyerabend, who was at that time still at UCL's History and Philosophy of Science department. And I was told I really ought to go to this seminar. It was a series of about 6 seminars, each one of them giving, they spoke alternatively. But the thing about it was the theatre of it, because they were both very forthright. In the discussion periods, no punches were pulled. They were respectfully but quite fiercely critical. And I've never forgotten that. I found it very interesting. It was so different from the conversations that took place between members of the department, the philosophy department, when they disagreed. But despite the ferocity, after the seminars, they went together to the Houseman room to have refreshments and so on. We knew it was okay. But still, it was quite... I was an undergraduate. I'm sure that most of it went over my head. I can't remember, but it was great. Okay, that's a little bit of context. I just want to kind of reinforce some of the things that have been said. Look at these dates. 1961, the thesis. Out of that grew Proofs and Refutations. And that was published a couple of years after Lakatos's death, 1974. But now the context. Okay, this is already, you mentioned the big 3, but look at these dates. Logicism, Frege, 1893, towards the beginning of the century, what was 90 years here, up to Wright in initiating neologicism, back to Frege, then formalism. You get clear expositions of a formalist position in Hilbert 1922, but then after the discovery of the independence of the continuum hypothesis by Cohen, you get a kind of resurgence of formalism. Cohen himself and Robinson, Abraham Robinson. This is in the late 60s now. Intuitionism, Brouwer, well, he was writing for a long time, but first in 1912, I believe, and then you've got a kind of a great resurgence of interest in intuitionism with Donnett's publications. So this is most of the 20th century and more. And if you look at other things that were very influential in philosophy of mathematics in the 20th century, other writings, you've got Putnam with these 2 papers, especially Models and Reality, although I don't know how much that was written about. And then Benacerraf, What Numbers Could Not Be, 1965, Mathematical Truth, 1973. People today are still writing papers on Benacerraf's problem here. So this is 20th century philosophy of mathematics. This is the context. But the thing about, okay, so the context, almost an exclusive focus on the logic and metaphysics of mathematics. Not entirely, because Quine was big and he had a very strong logical view. And an almost total acceptance of the axioms, definitions, theorem, proof, schema of mathematical progress. Obviously, I'm oversimplifying here, but that's the context. And then you've got Lakatos's alternative here. Lakatos focuses on the advance of mathematical knowledge, and he rejects this axioms, definitions, theorems, proofs scheme as far from adequate. And here is some of what Lakatos explores that's ignored by the standard approach. Finding appropriate definitions and conjectures for proving, checking a proof attempt to see if it is in fact a proof, how to proceed upon finding a proof attempt to be a non-proof, things like that. Okay, didn't really get discussed. So now, this is a kind of reaction. If you ask me to find this in print, I don't think I can do that. But I know from my own experience and from my own earlier attitude, this is what we would say, it's merely heuristics, meaning it's a matter for psychologists, or sociologists possibly, but not for us. Okay, at that time I didn't know about polio. But of course it is in part heuristics, but what is the word merely doing there? It's what we were doing was constricting our view of what was proper philosophy or epistemology of mathematics. And I would say that Lakatos's heuristics were concerned with how discoveries can be made, as well as how justification can be achieved in practice. And so his inquiry falls within epistemology of mathematics. Okay. You can't sweep it away into the psychologist's bag. So now I'm just going to, Cauchy's. So in his famous book, he examines Cauchy's argument for Euler's formula for polyhedra, and uses the history of responses and counter-responses to the argument to find methodological answers to some questions which are occluded by ADTP blinkers. And this work, I say, falls within the philosophy of mathematical practice. Okay. And I would say, in defense of the preeminence of Lakatos here, is that he is the first major philosopher since the rise of logic-dominated philosophy of maths to focus on mathematical practice. I think that's fair. When you think about all the philosophers that said something about mathematical practice, you've got Descartes did, Leibniz did, and Plato did as well. He criticized geometers for always being content to rest their arguments on hypotheses. I remember being struck by that. But now, let's look at the dates. 1961, he presents his seminal PhD thesis, out of which proofs and refutations and later work grew. 2008, you get the landmark collection edited by Paolo Mancosa that Brendan Fenner and Colin mentioned. Then you've got, in 2009, an international group of researchers meets in Brussels to initiate the Association for the Philosophy of Mathematical Practice. And 2011 was the inaugural meeting of this association. That's 50 years later. Okay, so it's a matter of the profession. Do we say philosophy of mathematics is a profession? Catching up with Lakatos. So yes, he was the first in this respect. Okay, so now let's get to something with a bit of substance, non-historical substance. I mean, I'm going to run through. Can give you a very quick account of proofs and refutations in order to link it with something that's much more recent. Okay, so here it is. If you have a conjecture, set out to prove it and to refute it. When you have completed a proof attempt, inspect it to make a list of all non-trivial lemmas it depends on. Okay, they might not be made of list. Search for counterexamples to the conjecture, those are global counterexamples, and to the lemmas, local counterexamples. Okay. I gather lots of you have read this stuff. I'm just reminding you. So you've got it in mind. Okay. If you find a global counterexample C, find all lemmas also refuted by C. Lemmas to which C is also a local counterexample. And here, Lakatos makes a kind of stipulation, he calls it a demand, that any global counterexample should be provably local. So, if you've got refuted lemmas, you replace the conjecture with one which incorporates, you replace the conjecture, which is the proposed theorem, with one which incorporates the refuted lemmas as an antecedent condition. Do not dismiss counterexamples as monsters, no monster barring, or shrink the domain to exclude them, no exception barring. I don't know why he didn't say no domain shrinking. Here, so now what's happening here is he's saying you can modify the conclusion to reach a genuine theorem. Okay? And this is part of the progress of the advance. If you have a local example, check to see if counterexample, check to see if it is also a global counterexample. If it is, revise the conclusion by lemma incorporation, as in 2, as in the previous case. If it is not, seek a replacement for the refuted lemma that will restore a path to the conclusion. Okay, so in this case, you are modifying the argument to reach a proof of something, okay, a proof of the current conclusion. But of course, you may later want to modify the conclusion yet again. Okay, so you've got this dialectical process going, very neat. Now I want to, so that's the nutshell. Okay. And I'm going to link it up to something which also coincides with it at this point with this demand that any global counterexample should also be a local counterexample. Okay, so this is now from a paper, I think a very good paper, called Rebutting and Undercutting in Mathematics by Kenny Iswaran, published in 2015. Okay, so it's not quite current, but it's quite recent. And what Kenny's doing here is he's trying to use epistemology of mathematics, abstract epistemology of mathematics, as we find it in the writings of Pollock. And he's going to try and use this to get clearer about what actually goes on in the equation. If R is this is rebutting now. If R is a reason for believing a proposition P, R can be rebutted by getting a more certain reason, S, to believe not P. And in the case that we're interested in, let R be a proof attempt of a mathematical claim P, S a clear counterexample to P, then S is a global counterexample and rebuts the proof attempt. Okay, this is the language Kenny's using. Undercutting, in contrast to rebutting, is this. If R is a reason for believing P, R can be undercut by getting a more certain reason T to believe that R is not an adequate reason to believe P. So in our case, let R be a proof attempt of a mathematical claim P, T a counterexample to a possibly tacit lemma of R, then T a local counterexample undercuts the proof attempt. And he gives a case. Cauchy gives a proof that the limit of a convergent series of continuous functions is continuous. I put it in inverted commas because whether the argument is proof, of course, is contentious. And Abel notes a global counterexample, which is this convergent series of continuous functions which has a discontinuous limit, the sawtooth function. Here I can show you on a little slide. The fourth element in this series is here. I've written it out. And the limit of the series is the sawtooth, which is a Fourier series expansion of the function y equals x over 2. And here is the picture. I've just taken this straight from Kenny's paper. You can see the sawtooth is continuous, of course. And so, but of course you can't really see that the fourth in the series is continuous. But it looks that way. But that gives you an idea. So now, so that's a rebutting. Abel's counterexample is a rebutting counterexample, or a global counterexample, to use Lakatos's term. And an undercutting case, we have for Kemp's attempt to prove the four-color theorem, and that was in 1879. 11 years later, he would find a local counterexample, a subcase of a subcase, which Kemp's method fails to show could be four-colored. So it's not a global counterexample, as you know. The theorem is true. Now, why is Iseron concerned about this? Well, he's concerned with what is and what should be required of an argument to be submitted or accepted for publication as a proof. If you're presenting it as a proof, it should meet this certain conditions. It doesn't have to be a strictly formal valid deduction or anything close to that, of course. And Iseron says it needs, among other things, enough detail. The argument needs enough detail that any rebutting defeater could be converted into an undercutting defeater. In Lakatosian terms, any global counterexample could be shown to be a local counterexample. Iseron calls this requirement convertibility, and he illustrates this using the Cauchy-Abel case. He shows how you could convert it. Well, this isn't quite fair to Cauchy because there's a dispute about whether the argument that's presented as Cauchy's now was his real argument. And Lakatos himself wrote a paper, Cauchy in the Continuum, well worth a read, where he argues that Cauchy was thinking and writing in terms of infinitesimals. On that ground, it looks as though it can be argued that the functions in the series were not continuous. Okay, so because anyway, that's a side issue. So I shouldn't have got drawn into that, but it's an interesting question. It's just not straightforward. It looks like, if you accept the way that Abel's argument is presented now, there's no question that Abel's counterexample was a counterexample to Cauchy's supposed argument. So anyway, Iseron says convertibility, enough detail that the argument has to have enough detail that any rebutting defeater could be converted into an undercutting defeater. So any global counterexample could be shown to be a local counterexample, and this is convertibility. Iseron acknowledges that his account lines up with Lakatos. If there are global counterexamples that are not local, then the proof is not convertible in my sense. my requirement of convertibility lines up with Lakatos's ideal of the proper development of the proof analysis. As far as I can see, Isorin's convertibility is just Lakatos's demand of retransmission of falsity. Any global counterexample should also be provably local. And it may be that Isorin actually got it from Lakatos, but it's also quite likely that Isorin thought it up himself. And he just rediscovered this bit of Lakatos. Maybe he came up with it and somebody said, yeah, it's already there in Lakatos. But Isorin is quite generous. Lakatos quotes him, quotes at length. So there's nothing wrong going on here. Now, the point of this is it's got a practical point here. We should be able to work through the proof attempt until we find the lemmas contravened by a global counterexample C. And if we cannot find any such lemma, we must add a suitable lemma to the proof analysis. That's what Lakatos says. We must increase the level of detail. Okay, so now all that was by way of showing you that Lakatos' stuff, his stuff, isn't just dead historical stuff, which nobody pays any attention to. And I can give you other evidence that philosophers of mathematical practice are taking Lakatos' stuff seriously today. So now I'm going to talk about something that I've been interested in for a while. These are intuitive arguments of a certain sort. And I'm calling them pre-proofs because people say, well, intuitive arguments, this is a huge bunch. You're only interested in a certain class of them, which is true. And so I'm giving them this fancy name, intuitive pre-proofs. They're intuitive arguments which, to those with relevant expertise, are convincing but are not proofs. And these arguments often involve the use of diagrams and sensory imagination. I know, I agree, but this isn't much of a characterization. It's very loose and so on. And I confess I can't do much better than that. So this is work in progress. Okay. But now I'm going to try and give you the idea with an example. Not a very good example, but this is one I use because I know that everybody here will have the relevant expertise. The proposition is this basic proposition of number theory. For any integers a, b positive, there are unique integers q, r, for which a equals qb plus r, where r is 0 or between 0 and b. Okay. And here is the argument. The integers can be represented as a line divided into intervals of length b units. Okay. And let a be any integer. A either coincides with a multiple of b or it falls between multiples of b. If a coincides with a multiple of b, then we get a equals qb plus r for 0r. Okay, so that conforms. Or a falls between multiples of b, as I have it here. Let's just magnify this a bit. If it falls between, then you've got a equals qb plus r, where r is strictly between 0 and b. Okay. And that also conforms. Put those two cases together and you get the theorem. Okay. Very quick, very intuitive, and without even worrying about whether that's a proof or not, you can be convinced by such an argument. Someone could be. It's the kind of thing I find convincing. Okay. But is it a proof? It's not a proof, I would say. because first of all, I'm assuming this disjunction A coincides with the multiple of B, or A falls between multiples of B. But what about this possibility? A is less than all multiples of B. Now, if I'm thinking visually in terms of this line, that's just not going to occur to me. Configurations in which the red vertical mark representing A is left of all the black vertical marks representing multiples of B are blocked out of our thinking in following the argument. It's not that we consider these possibilities and say, no. Okay? It just doesn't occur to us. So you might say, Lakatos, well, it's a hidden lemma. We're assuming it's hidden. For any A, B, and Z would be positive, there is some Q such that QB is less than A. Here is a second problem. A falls between multiples of B, so A equals Q B plus R, where R is strictly between 0 and B. This actually is an inference. Here, you say A falls between multiples of B, therefore there are unique Q and R such that R falls between 0 and B, and A equals QB plus R. Now this actually is invalid unless there is a greatest multiple of B less than A. Configurations in which there is no rightmost black mark to the left of the red mark representing A. These are blocked out of our thinking. It's not that we would, in the course of it, consider this and give reason for saying it's wrong. So again, the possibility that there's no greatest multiple of B, it just doesn't come to mind when we're going through the original argument. So the argument has another hidden lemma for any A, B. In Z, B positive, this set, the QB's less than A as the greatest number. So now I am insisting on the distinction between merely unstated lemmas and hidden lemmas. Perhaps there are more distinctions I need to draw here, but definitely these two, because merely unstated lemmas are almost always there. And that's fine when the intended readers can be expected to know or work out the relevant lemmas. And here are a couple from basic maths. I'm saying that these hidden lemmas, even if they're not very deeply hidden, are not merely unstated. Something stronger than that. Perhaps I need to make a distinction between the deeply hidden lemmas and not so big. I can't do that in a satisfactory way yet. Okay. So now I've given you my reason for thinking. It's not a proof. But why is the argument reason for confidence in its conclusion? I mean, if you're the audience and the person who's presenting this argument is an expert, you might have your confidence in the expert's intuitions as your reason for confidence in the conclusion. But what I think is going on here, where there's no separation between you and the experts, our prior grasp of the structure of integers justifies confidence that the visuospatial configuration that we were using, given the way that we interpret it, represents veridically the relevant arithmetical situation. The non-trivial lemmas hidden by the visuospatial representation are in fact correct, as it turns out. Okay, I just give you couple of other examples of intuitive pre-proofs where it's much harder to dig out the hidden lemmas in order to get a proof. And here, I'm just going to talk about the Thurston case very quickly, because that's what kind of stung me into investigating this question of intuitive pre-proofs more. He's giving a lecture at a conference on the Poincaré conjecture. And he says, even 5 minutes into his lectures, we have a very strong, clear, beautiful picture for three manifolds, a decomposition into canonical geometrical pieces. This is what his geometrization conjecture is. We had extremely convincing evidence for the picture even before Perelman's proof. For me, more than 99%. That convincing. And my initial reaction to that was, how can anything short of a proof warrant such high confidence? And then I found that I myself could have confidence as a result of non-proofs, intuitive non-proofs of a very simple kind. I mean, I couldn't even have the intuitions or the intuitive thinking that Thurston was having. Okay, so I've got to wrap up here. I will wrap up and skip some stuff which may come out in the discussion. Thank you for listening.